Hi everyone. In this lecture, we will discuss how to apply Miller's theorem for MOS based circuits. Okay, so we'll start with the first circuit shown here. We have a MOS amplifier between gate and drain. We have connected a capacitor of value C. We are interested in what is the input impedance of the circuit. Okay. So, if you want to apply Miller's theorem, you need to know the voltage at the input port here, which is Vi. At the output port, assuming the MOSFET has a finite output resistance given by R0, so the gain is simply minus GM R0, and the input impedance, or at least the input as seen by the input, you will see an impedance given by this equation. So, if I apply this, it's going to be ZF by 1 minus of minus A, it's going to be 1 plus GM R0. And in this case your ZF is simply 1 by SC. So you will see an increased value of capacitance. Your impedance reduces by 1 plus GMR0. Your impedance, because it's becoming ZF by 1 plus GMR0, which means impedance is reducing, which means capacitance value is increasing. So it is 1 plus C will be multiplied by 1 plus GMR0. But then we should realize that if you actually simulate a circuit like this and try to find its input impedance, it will not be a pure capacitive impedance. Okay, so if you just try to plot the input impedance here, you should expect to see a plot this way, but you will not see that. Okay, so we will discuss why is it not that, why is that not the case? What are we actually missing here? So the main point to understand here is, for the Miller effect, this node voltage here has a perfect relationship with the input voltage, which is it is minus GMR0 times Vi. At the output port, we assume for a Miller theorem, the output port is actually represented by a dependent voltage source. But we need to realize MOS amplifiers are all transconductance amplifiers. So they are modeled by dependent current sources. So then how do we modify the Miller's theorem so that we can apply it for MOS based circuits? So that's the topic of this lecture. So we'll start with the simplest model, where here I have shown a MOS, that is, you have a transconductor. So the output port between the output, two nodes at the output, instead of a dependent voltage source, we have a dependent current source given by Gm times Vi, where Vi is the input voltage here. Now we need to see what is the input impedance for this. If I want to apply Miller's theorem, or what will be the input impedance? As seen by the input, how does the circuit look like? For a conventional Miller theorem, just to recall, you will see an impedance of ZF by 1 minus A being the gain at the ratio of the output port voltage to the input port voltage. But now, if you find the input impedance here, the current flowing through the dependent source is the same as the current flowing through the impedance ZF. So which is nothing but the same current that is flowing through the input voltage source as well. So as far as the input is concerned, it's always going to see it as an input impedance of value 1 by Gm. Which means the result here, the input impedance, is completely independent of what you've connected between the two nodes, between the input and the output nodes. Okay, it's independent of ZF. ZF has no effect at all in this circuit. Why is that the case? We'll try to mathematically derive some expressions for that. So to begin with, this is what we call as the transconductance amplifier model. And we said most MOS amplifiers are better approximated as transconductance amplifiers. Okay, so where at the output you have a current source, is a controlled current source given by Gm. Gm is the transconductance, and ZL is the output resistance, total output resistance. I've just modeled it as a load resistance, clubbed all the resistors together. They are seen at the output port as ZL. So this is a model which better approximates MOS amplifiers. Now what we are going to do is that we will now connect a feedback impedance, that is ZS, between the input port and the output port. I've just called it feedback impedance. It's just an impedance between the Miller impedance, rather we'll call it that way, ZF between the input port Vi and the output port V0, of voltage V0. And then we'll see what happens to the input and the output impedances. So to see that, I have actually shown here, this is the equivalent circuit, and which better approximates a MOSFET. And now we are interested in MOS based circuits. We are interested in finding what is the input impedance. So now what we will do is we we'll apply the standard trick, which is, this is a Norton equivalent, a current source and resistance in parallel. We'll just model this as a voltage source and resistor in series. So you can simply find the open circuit voltage, and that voltage will simply be equal to minus of Gm times ZL. So that will be simply minus of Gm times ZL into Vi. That will be the open circuit voltage. And the impedance seen at this node is found by making sure this current goes to 0, and that is simply equal to ZL itself. So I've drawn the Thevenin equivalent for this and shown here. So this is the Thevenin representation between these two nodes. Okay, current source and resistor in parallel is shown as a voltage source, a dependent voltage source, and impedance in series. Now, this problem, we have now reduced this, if you recall from the previous lecture, to a problem where the dependent voltage source has a finite output resistance. So all I can do is I can just simply club this resistance along with the impedance ZF. So then you get this circuit. Once you have this, this is your familiar Miller's theorem circuit. So wherein this is where Miller's theorem is applicable. The output voltage has to be a dependent source for you to apply Miller's theorem. Okay. So then the node impedance connected between the two terminals, between the input and the output terminals, okay, as seen by the input, gets divided by the gain. So we see an impedance of value ZF plus ZL by 1 plus GM ZL, where GM ZL here is nothing but the gain here. So I've written it as minus AVI here. A is nothing but GM ZL. So that's what I've shown here. Okay. So you are going to see ZF plus ZL here, I've shown it here, divided by 1 minus A. A in this case happens to be 1 plus A, because this is minus A here. So you will see whatever is connected between the input and the output port, that will get divided by 1 plus A, and A in this case is 1 plus GMZL. And at the output, you are going to see ZF plus ZL by 1 plus GMZL. So this is what we call a Miller's theorem for, or a modified Miller's theorem for transconductance amplifiers. So this is what we should be using when we are analyzing MOS based circuits. Okay, so the expressions look a little bit complicated, but when you think about it, it's pretty intuitive, because in this case of when you actually analyze circuits with the transconductance amplifiers, the output voltage is a strong function of what you connect at the load. Okay, so here as we saw, the gain here, in case when you converted it to a Thevenin equivalent, is a strong function of what you connected at the load, because it's a current source at the output, a controlled current source at the output. So therefore the voltage, the output voltage, has to depend upon what you connect across the load. Okay, and when you apply Miller's theorem, you will see that the gain and the input impedance seen at the input both will be functions of the load resistance, which was not the case when you had a dependent voltage source. Okay, so this is the main difference between transconductance and voltage amplifier models. So I'm just trying to show the input port. As I said, the input impedance is of greater significance, which we will discuss once we start discussing the frequency response of single stage amplifiers. What happens to the input port is that the input impedance can be now split up into two parts, which is, it's actually ZF plus ZL divided by 1 plus GM ZL. Okay, so this additional term, this term, the dependence on GM ZL, actually is because of the transconductance model. Okay, so I can split this as two resistors, which is ZF by 1 plus GM ZL. So this is what we should have ideally expected. Okay, so GM ZL is simply the open circuit gain of this amplifier, or if you convert the transconductance amplifier into a voltage amplifier, okay, so then I can simply represent the voltage gain as GM into ZL. But the factor ZL is also coming into the picture because it's a transconductance amplifier. So which means the input impedance now is a very strong function of what you connected at the load. So that's the main difference, that we will see when we apply these results to transconductance amplifiers, when you apply Miller's theorem to transconductance amplifiers. We will now go back to the circuit which we started, and then we wanted to analyze this circuit using the equations that we have derived so far. Now, if you want to find the input impedance, first we'll start with the easier case, which is lambda equal to 0, which means R0 is infinity. In that case, when you apply a voltage Vi, you will have a current GMVi flowing through the MOSFET. And since R0 is infinity, this GMVi as it starts flowing from drain to source, it comes here and sees no other path to flow. So the only path it will take is through the capacitor, and that is same as the input current drawn from the voltage you apply. I mean, the current through the gate is 0, so the entire current II, which is the input current drawn from the voltage source Vi, will exactly be equal to GMVI. Okay, so then the input impedance seen is simply, this is 1 by Gm. The input impedance seen here will simply be 1 by Gm. Now, we will try to mathematically analyze this using the results we have derived. Okay, so what we will do is that the MOSFET model is the same, which is GMVI, R0 is infinity. Okay, and we have connected between the input and the output port an impedance of value ZF. And I'm going to assume that there is an imaginary load impedance ZL, and I'm going to tend ZL to infinity in the analysis. So using our expressions for the input impedance as seen by the input, it's going to be ZF plus ZL by 1 plus GM ZL. So the expression is ZF plus ZL by 1 plus GM into ZL, where GM is the small gm here, the MOS transconductance. So I have split the impedance as two parts, which is part of it containing ZF and the other part of it containing ZL. Now, as you tend ZL to infinity, since ZF is finite, for a finite value of ZF, this value will tend to 0. So there is no contribution from ZF. That's what this is telling us. And then in this expression, when I tend ZL to infinity, this is nothing but, if you see this is nothing but ZL in parallel with 1 by Gm. So if I ensure ZL as infinity, you are simply going to get 1 by Gm. So that's why the input resistance Zn, or seen at the input, I am going to call it Zi of S, is simply equal to 1 by Gm. Now as far as the output port is concerned, the current source GMVI, okay, is now going to see, I can represent this current source as a voltage source and resistance in parallel, okay, or at this node I can see what is the impedance seen, and that is going to be ZF plus ZL by 1 minus 1 by ZM ZL. Now as I make that ZL tend to infinity, this value will tend to infinity as well, because 1 by Gm plus ZL will tend to 0, okay, so and you will be left with ZF plus ZL. Since ZL is infinity, the impedance will be infinity. So the model will simply reduce to something like this. So I can now see the whole idea of applying Miller's theorem is to treat these two output and input nodes as two non-interacting nodes. Okay, the moment we connect it this way, the moment we actually put an impedance in between ZF, we expect it to change, but look, if you look at this, it really hasn't changed. I mean, the output port is still, you're drawing a current Vi, at the input port the GMVI, and input port the current is same GMVI as well. So ZF really has no effect. In fact, ZF has an effect, in the sense that what I meant by ZF has no effect is that even if you change ZF, the input and the output impedances are not going to change. Okay, the impact that ZF had was that it created some kind of feedback between the input port and the output port. So it fed the current, whatever GMVI was flowing at the input, at the output, back to the input. So that's the effect. It's an indirect effect. Okay, so we'll talk about that later, but right now, purely when you're analyzing the circuits, I just want to give a mathematical expressions and leave it here, and we will draw the intuitions once we start going into the analysis of single stage, the frequency response analysis of single stage amplifiers. So this is the model for this amplifier, for this MOS amplifier with R0 equal to infinity. Now we will consider a finite R0. In that case, ZL will be equal to R0, okay, and ZF will be equal to 1 by SC. In that case, I'm going to use the expressions as it is. So this is ZF plus ZL by 1 plus GM R0, and that if I split it into two parts, I'm going to see 1 by SC into 1 plus GM R0 plus R0 by 1 plus GM R0. So this term is nothing but R0 in parallel with 1 by GM, which can be approximated to 1 by GM. Now if you see, this is nothing but a capacitor and resistor in series. The capacitance value is C into 1 plus GM R0, and the resistor value reduces by R0 by 1 plus GM R0. Okay, so now it's a series capacitor. So if let's say there were only a capacitor, the impedance as a function of frequency would be just, I'm plotting it on a log scale, so it will just linearly go down to 20 dB per decade. But now, since it's a series RC circuit, so the resistive impedance, it's independent of frequency, it's given by R0 by 1 plus GM R0, So which means the overall curve is going to look like this. So it's going to behave like a capacitor for a certain frequency range, and then it's going to behave like a resistor. Okay, so since the two elements are in series, the one with the larger impedance will dictate the overall impedance. So the point where this intersection occurs is what we would call, here in this case it turns out to be 0. Again, I'll come to zeros and poles a little later once we start with the proper discussion of frequency response of amplifiers. The point where the transition occurs is when the capacitive impedance, which is 1 by C into 1 plus GM R naught, starts becoming equal to the resistive impedance, and that point will be 1 by C R naught. Okay, so this is a more exact model for the input impedance if you use these exact expressions. So the input impedance also has a resistive component, and this is because of the load resistance. So for frequencies less than 1 by 2 pi R naught C, which is in this region, you are in this region in this graph, what I've shown here. When you are in this region, you are going to see this like a capacitor. So it will just going to look like a Miller multiplied capacitor. So this capacitance is going to be 1 plus GM R naught. So this phenomenon is called Miller effect. Okay, the multiplied capacitance, you are going to see a large capacitance. So this is 1 plus GM R naught. The value of the capacitance is 1 plus GM R naught. At frequencies much greater than 1 by 2 pi R naught C, which is at very high frequencies, you are going to see a resistance of value, because it's, if you look at this figure, it's just going to behave like a resistor. Okay, the capacitive impedance is so small that we can ignore it at high frequencies. Okay, so then the resistor value is going to be approximately 1 by GM. That should make intuitive sense, because if you look at it, I've just shown here, if you look at this circuit, the moment we apply a voltage, that's the input excitation Vi, the MOS is going to carry a current GMVI here. Now this GMVI current, as it enters the drain node, as it reaches the drain node, it's going to see two impedances. On one side it will see a capacitor of value 1 by C, other side it's going to see an impedance of value, resistance of value 1 by R naught, just R naught. But at frequencies lower than 1 by R naught C radians per second, or 1 by 2 pi R naught C, the resistance offered by R naught is going to be much smaller. So most of the current will flow through the resistor, and it's going to create a voltage drop of value minus GM R naught. So little to no current will flow through the capacitor. There is a path for the current, so the current will take, always it chooses the path of least resistance. So it will choose to go through the resistance R naught. So you'll have a voltage of minus GM R naught, and then the voltage appearing across the capacitor will be 1 plus GM R naught. Okay, so now you can directly derive the input current. So Vi minus the input impedance seen here, II, is going to be Vi into SC minus, the voltage between the voltage across the capacitor is going to be Vi minus of minus GM R naught times Vi, the whole thing times SC. So you will see a multiplied capacitance here. So Vi into SC into 1 plus GM R naught. Okay. So this is your multiplied capacitance. At very high frequencies, of the current as shown in this circuit here, you have a current GMVI. Again, it sees two paths, R0 and 1 by SC. But now capacitor offers really low impedance. So most of the current GMVI is going to flow through the capacitor. Okay, and so since it's going to fully flow through the capacitor, so the input impedance, the input current drawn from that will also be same as the current flowing through the MOSFET's drain to source. So this is GMVI. You can also say that in a feedback point of view, when we discuss feedback, I'll discuss this in more detail, that most of the current the MOS is carrying is fed back to the input. Intuitively, we can see that at high frequencies, capacitor will behave like a short circuit. So this node is shorted like this. So you're looking at this node, and there is an R0 here. So this is nothing but the diode connected MOSFET with a resistance of 1 by GM in parallel with R0. So you will simply see 1 by GM in parallel with R0. So you can directly see it that way. So at high frequencies it will be 1 by GM R0. Low frequencies it will be a Miller multiplied capacitor. Okay, and when I'm saying Miller multiplied, it's a large capacitor. So I'm just calling it as a Miller multiplied capacitor. Okay, so this is more of a rigorous analysis. We will see even more applications of this result in when we start discussing the frequency response of common source amplifiers. So the main take home point here is this expression is the analysis, is the expressions that I've shown here. Okay, especially the input impedance is of very importance here, is of great importance here. It's going to be ZF plus ZL by 1 plus GM ZL. So this is the modification that we have to do when we apply Miller's theorem. If you want to directly apply Miller's theorem to transconductance MOS amplifiers, which happen to be transconductance, better approximated as transconductance amplifiers.